Ask, so I'm a normal person again. And I would like to give you the famous 18 minutes, 20 minutes minus the 2 minutes that these other fellows, on the question, or give you an overview on this presentation, the 50th anniversary of the Hadron Collider at CERN. Now, I will start with Rolf Widerooy. Widerooy is the inventor of the collider, has been the progenitor of many particle accelerator concepts, including the Betatron and the linear accelerator. His concept of colliding two particles beam head-on in a storage ring device in order to increase the interaction length with respect to a stationary target has been described in his 1943 patent. The usual invention format has been motivated by the exceptional circumstances of Germany during the war. And here you can see the picture of the official patent of Widerooy, presented here, and it's a patent which was written in 1943. The principle of the colliding beams, Rolf Widerooy decisively influenced the course of high-energy physics, with Betatrons shaping the landscape in the early days, and linear accelerators and colliding beam becoming indispensable tools today. Here is the example of the picture. You can see particles accelerating in a ring, are separated into counter-rotating rings where the collisions are observed. Widerooy moved to Switzerland in 1946. He's also been a CERN consultant, by the way, at the time of the alternating gradient focusing principle for the 26 GeV synchroproton. I also had the pleasure to meet him personally many times, together with many other people which are here since early days. Another important point to be mentioned is the one Bruno Tuschek. Amongst the key players was Widerooy's assistant, the Austrian Bruno Tuschek, 1921-1978, which died at age 57, a victim of the Holocaust since his mother was Jewish. During the death march from the Hamburg prison, Tuschek was shot by the SS officer, presumed being dead and thus left behind, fortunate still alive. He lived permanently in Italy from 1958 until his premature death. In 1960, he gave a talk in the Frascati where he described the idea of a collider, a particle accelerator where a particle and its antiparticle collide with the same orbit in opposite directions. The first electron-positron storage rings, called Anello di Accumulazione, ADA, was constructed in Frascati under Tuschek's supervision in the early 60s, followed by the construction of Vadone. The Spear collider under the SLAC Linear Accelerator Center was completed in 1972, and it soon contributed to discoveries of the Psi-J meson and the Tau lepton, both recognized with Nobel Prizes to Sam Ting and Bernd Richter and to Marty Pearl. The initial discovery has been the one of the story is the muon neutrino. The water rewarder was carried out in 1960. The muon is a relatively heavy, charged elementary particle which was discovered in cosmic radiation during the early 30s. In the view now accepted of the paired grouping of elementary particles as the truth in its Presswinner's discovery. The Nobel Prize in 1988 was awarded jointly to Leon Lederman, Mel Schwartz, and Jack Steinberger for the neutrino beam method and the demonstration of the double structure of the lepton through the discovery of the muon neutrino. The experiment was planned when the three specialists were associated with Columbia University in New York and carried out using the alternating gradient synchrotron at the Brookhaven National Laboratory at Long Island, however, still with a fixed target proton. Another important step has been the experimental discovery of the neutral current at CERN. In 1973, the so-called neutral currents were discovered in the neutrino reaction at CERN and promptly confirmed at Fermilab. Experimental observation in neutrino interaction proved that besides then hypothetical weak interaction mediated by the charged boson, plus and minus, there was also a neutral electromagnet weak partner, the Z0. This was, no doubt, another Nobel class prize experimental discovery, which was discovered, was however never recognized, in my view, mainly because of the early death of André Lagarigue, which is here at the time. Now, the early progress of colliders were based on a number of steps. First of all, conceptual steps in Frascati and Novosibirsk. Frascati with Tuschek, Novosibirsk with Butker. two great scarcisms at that time, luminosity rates, in other words, a beam-gas background. The early success of the plus-minus colliders was the next step forward. The first proton-proton collider for high energy with the ISR is the beginning of a far more difficult physics. This is what we're discussing today. Two Swiss watches in collision was claimed at the time. The PP bar accumulation for high energy at SPS and the PM2 shift problem were major problems in the question. Fewer particles and higher tune shifts. The pessimism was conjugated with a widespread initial lack of confidence in hadron colliders in spite of the higher energies when compared, for instance, with the plus and minus. The first electron-positron collider, which is being discussed today, is discussed here today, is a stationary beam target with the total energy equal to this formula, 2e mc squared to power 1/2. The more effective colliding beam is set up, the two accelerated beams of energy have the energy, total energy equal to the sum of the energies. Gain rate is, first colliding beam was built early in the 60s, I said, Frascati and then Novosibirsk. Here is the picture of the ADA, the net accumulation, the first electron-positron collider. Construction is finished in 1961 and luminous detected in 1964. The first hadron collider began at CERN in 1966. The collider was operational in 1971. And here is the picture which everybody knows today, the purpose of today, to show this picture. The first hadron collider. The radius of the ring is 150 meters with 8 crossing points, 2 counter-rotating beams at an angle of 15 degrees. The highest energy was 63 GeV. You can see here the picture of the event. A stack of DC current up to 50 amps has been stored with the protons at the CERN PS. So the progress with the first hadron collider has been very important. Hadrons rather than electrons were necessary in order to further extend the domain of particle energy. The ISR has been the world's first hadron collider, and from its initial setup, the collider itself has the capability to produce particles like the psi-J and the upsilon, as well as the observable jet structure. However, the particle detector experiments were not configured to observe events with large momentum transverse to the beamline, leaving the discoveries to elsewhere. The advent of the ISR involved many advances, however, the advent of the ISR involved many advances in accelerator physics, including the first use of the stochastic cooling. It held a record for luminosity for a hadron collider itself. The next step was to transform an existing accelerator in a collider. In 1956, back in time, Klein with myself have proposed to modify the proton accelerator into a proton-antiproton collider. At the time, a proton accelerator, which was already running at Fermilab, it was under construction at CERN SPS. The scheme was proposed both at Fermilab and CERN, and was ultimately adopted at CERN for the SPS. The program was approved in 1978, and very, very fast, because the first W were discovered at the beginning of 1983. And here's the example of the evolution of these events as a function of time. These important experiments have been the collider, the initial cooling experiment. This was 1977. In a record time, in 9 months, the magnets of the G-2 experiment were modified and used at CERN to build the proton-antiproton storage ring, the initial cooling experiment, ICE. It served for a verification of the cooling method to be used for the antiproton project. Stochastic cooling was approved the same year. Electron cooling followed later. Electron cooling was provided by an electron cooler located in the straight section of the ring. With some modification, the cooler was later transplanted into LEAR, low energy antiproton ring, and then, with further modification, into AD, antiproton decelerator, where it cools antiproton also to this day. Here's the picture of the proton accumulator. And here is the picture of an event of an antiproton cooling in 2 seconds resulted from this activity. Now, the experiments were many, but the most important one related to this subject were UA1 and UA2. The program was initiated in 1979 at the CERN proton-antiproton collider. The SPB-S became operational in July 81, and by June, as I said, in June 1983, the discovery, the W and the Z were announced. Myself with van der Meer, we received the Nobel Prize in Physics by the Nobel Committee for their decisive contribution to the large project, which led to the discovery of the field particle W and Z. The number was given to myself for his idea to convert existing large accelerator into a storage ring for proton and antiprotons, i.e. the concept for the PB bar S, and to Simon van der Meer for his ingenious method for dense packing and storage of proton, now applied for antiprotons, i.e. the device or the technologies for stochastic cooling. The conception, the construction, the operation of the SPB bar S were considered a great technical achievement at that time. Now, the C mass determination is an example of this you have shown here. You see how beautiful the result is. You can see here as a function of in the channel W electron-neutrino channel, the number of events is a function of the energy of the event, and you can see the beauty of the result, and the mass of the W was discovered in this way to be 80 MeV, 80 GeV of mass with this tremendously accurate value. Together with the experimental program, there were advances in the theory. Following the symmetry breaking paper by Peter Higgs and François Egler, in 1964, Steve Weinberg and Abdus Salam applied the Higgs mechanism to a model for electroweak symmetry breaking for the interaction between the scalar boson and the electroweak symmetry theory. For this achievement, Salam, Glashow, and Weinberg were jointly awarded the Nobel Prize in 1979. For their contribution for the theory of the unified interaction unified weak electromagnetic interaction between elementary particles, including inter alia the prediction for the weak neutral current, the Z0 particle. The theory and the Nobel Prize required also another new massive particle, neutral particle, the Higgs, to be detected experimentally. The next story, part of the story. Here is a picture showing theorists and experimentalists joining the Nobel Committee. You can see myself and Simon in the first row receiving the prize for the lie. And the second arm, you see also, you see also here, Abdus Salam, indicated from the picture. Here you can see Sally Glashow, and you can see Steve Weinberg celebrating 1984 Nobel Prize ceremony. The next important step was a connection from the model to a more complete theoretical description. During this year, very fundamental theoretical development took place after the idea of the Weinberg-Salam model. Veltman, Terry Toft, in 71 described a gauge which had a property that in all orders of perturbation theory, there are only a finite number of infinities, which can then might be absorbed into the redefinition of parameter essential to any true renormalizable theory. The theory might then be able to describe the weak and electromagnetic interaction energy far beyond accelerator and maybe all the way up to 10 to the 19 GeV, the so-called Planck mass scale. The Nobel Prize for Physics 1999 was jointly awarded to Veltman and Toft for elucidating the quantum structure of the electroweak interaction in physics. Now, here is a picture of the Gran unification point, which is still an open problem for today. A running coupling constant of the three main action may not simply converge in a common unified value. If you take the value at the LHC, you can see that in fact that they are still vastly separated without SUSY. It may be modified if there is a low mass SUSY, LHC energies, which may converge, may change the three components in order to reach a common result at a certain very high mass, which, by the way, is a mass which corresponds also to the nearly value of the possibility of the proton decay. No doubt the convergence of the three running company constant to a common value with the quark unification is probably inevitable. However, the mechanism for this change in mass values or this occurrence are still vastly unknown, and we have a lot of people here today which can converge and contribute to this point. Collider options were also possible in the United States. In 1974, Isabel, at 200 by 200 GeV proton system using a superconducting magnet was recommended for Brookhaven National Laboratory. By 1983, the US Department of Energy canceled the project after spending more than $200 million. The harbinger for the much more costly acceleration of the supercolliding superconductor occurred in October 1993. The project was cancelled in 1993 due to the budget problems after 22 kilometers of tunnel and the expense of nearly $2 billion. The BNL RC began operation in 2000, and until November 2010, it has been the most powerful heavy ion collider in the world. The LHC is operated with 25 years higher energy per nucleon. As for 1918, RIC and LHC are the only operating hadron collider in the world, but LHC uses mainly colliding protons and heavy ions only for about 1 month out of the year. And now the last point I'd like to discuss is the question of the latest Nobel Prize for CERN discovery. CMS and Atlas observed in 2012 at LHC a narrow line, a significance about 125 GeV. Peter Higgs achieved promptly the 1913 Nobel Prize in Physics. Experiment also excluded Higgs boson of more than less than 600 GeV. Searches have been performed in several decay modes, however, always in the presence of very substantial backgrounds. Experimental energy resolution has been also for much wider than any conceivable energy width. With the Higgs mass, the electron vacuum is metastable, but with a lifetime longer than life to the universe. No experimentally confirmed evidence so far for additional new physics like SUSY. And here is the picture, which is worth mentioning, the picture of Peter Higgs at CMS, a quiet man making a big bang. And here is the future of the Higgs, the LHC, the future of the LHC, high luminosity LHC. During the next 20 years, CERN plans to pursue a hadronic reduction Higgs-related sector and the possible existence of SUSY. The existence of additional Higgs particles is assumed to be unlikely within the CERN range. Therefore, the studies will concentrate on the property of the already discovered mass. The high luminosity LHC with already a short Higgs factory able to perform relatively accurate, typically 10% measurements. There are plenty of opportunities to check the coupling, since on the 125 GeV mass, and also includes, in particular, also the gamma-gamma events for most of the other channels. The proposals, next, the last point I want to mention briefly is the proposal of Higgs beyond LHC. While W and Z0 are vector, Higgs is a scalar, namely spin zero, at a much stronger coupling with the initiator with muons than for electrons. Two main futures are possible, E plus E minus colliders, and this can be a 100-kilometer ring or a linear collider, or mu-mu ring, which much lower cost and much shorter time schedule, and which can maybe easily fit within the existing site. But it requires a lot of development. And there are two possibilities of that. The S-channel resonance at a mass of 126 GeV, and the high mass collider events up to TeV to observe the rest of the events occurring in the system. But it's quite clear that the real problem is the development of R&D. The muon picture here is very quickly shown. You can see here how the cooling process is proceeding. There are three lines. First, the linear transverse cooling of mu signs and small delta P. Increased. Two is ring cooling 6D. And the third one is parametric resonance cooling, where the elliptical motion of space is becoming hyperbolic. You can see here the initial admittances in millimeter radiant and the final value after containing those effects, which certify the size of the collision. The leading processes for these events are quite, sorry, something broken here. They're quite beautiful. They remind the story of LEP and the Z0. You can see here the W going to the Higgs going to 2 Ws, the Higgs going to BB bar, and so forth and so on. And it gives finally a trigger luminosity which with 2 10 to the 12 centimeters squared per second minus 1, achieved with the 10 to the 12 muon per bunch. The Higgs rate is of 44,000 events per year in each detector. Now, briefly, the last point, there is a possibility of perform initially an initial cooling experiment, which is a practicalization appropriate cooling demonstrator. Sorry, it doesn't move. The goal is to prove experimentally the 3D cooling. Okay, it's not moving. Oh, sorry. Another facility, namely all the rest, will be added after the cooling experiment has been confirmed at a lower cost. And this is shown how the initial cooling looks like. It's a ring of 33 meters. And Of course, one has to realize that what we're all doing is a beginning of a much wider applications of accelerators. The giant research of CERN Large Collider in Geneva is only a tip of the iceberg. An accelerator can shrink a tumor, produce cleaner energy, spot suspicious cargo, make a better radial tire, clean up dirty drinking water, map a protein, study nuclear explosion, design a new drug, make a heat-resistant automotive cable, diagnose a disease, reduce waste, etc., etc. And medical industrial application today, making industrial application of the whole system of accelerator exceeds 3.5 billion per year, and other very large numbers are also indicated for various similar conditions. Conclusion, last word. Since the initial introduction of high-energy physics, the collider technology, first the CERN and the later Fermi Lab, has demonstrated the highest energy sector, transforming the two major existing accelerators into colliders with remarkable luminosity. The cooling technology has been generalized, and accumulated rate has been greatly increased, mainly with the help of Vandermeer cooling, later and also with Butker cooling, both at CERN and Fermi Lab. On the other hand, in the energy spectrum, very low energy PP bar, Lear, have permitted very fundamental discoveries. Equally revolutionary has been the association development on instrumentation with a 4-part hermetic detector like UA1 and UA2, Hadron calorimeter. Professor Schopper here today is a major contributor to this fact, and drift chamber, George Schapak, also Nobel Prize winner of '92 is an element, which have ensured that the statement that even Swiss watches a detection capability comparable with the passive items can be performed. Therefore, that's essentially, I will stop to that. Question block is block. Essentially, thank you very much.
Thank you very much, Carlo, for this very enlightening and also inspiring presentation, overview on colliders and their achievements. I look around if there is a question or a comment. If this is... Yeah.
Thank you, Carlo, for this nice talk. I don't see you anymore. What do you think are the chances to get a muon collider realized?
No, it's fine.
It's fine?
Time is up. We say 20 minutes.
No, but we have time for a question. There was a question
Okay.
on whether you see the chances that a muon collider can be realized. You want to give a short comment on this?
Yes. Well, when one talks about muon colliders, one has to look, first of all, of what kind of energy of muon collider one is talking about. There are some people which think about a muon collider in part of a new large detector, which will give you muon collider at many TeV, 3 TeV, 10 TeV, 14 TeV, whatever. This is something which, of course, will have to require a totally new situation in money and dimensions. This is not what I'm addressing myself to. What I'm addressing here is the specific case of realizing that while the W and the Z are vector, the Higgs is a scalar. And the Higgs scalar, the muons are winning respect to electron by a tremendous amount. So if you make a very simple detector, which can fit within the CERN facilities of today, using protons, or also ESS is another example, for instance, the possibility in Sweden. If you can take these events and try to look for events of the type in question, you can collect a very large number of events which can repeat the same beautiful mimics that we learn about Z0 and W with a lab, but we can do them with muons and also a possibility of this type. And this is seems to me something we can do easily, because the amount of construction is small, the resources are reasonable. It can be done with whatever money we already type of money we already have. And in my view, is I think next week we should do as quickly as possible in order to make sure that in fact we find for the Higgs the properties which are essential in order to explain that the Higgs is really what we think it is. Thank you very much.
Thank you very much, Carlo, and I pass the baton to Freddy.
Thank you, Carlo. Thank you.